In this video, we're going to explore the domain and the range of linear functions and quadratic functions, both given the equation and also the graph. But before we do that, we have to be familiar with something called interval notation. And this is a way that we're going to write answers to problems. We're going to write it as essentially not an inequality anymore, but a beginning and an end. Essentially saying we're going to look at this number first and then anything in between, and we're going to stop at this other number. So there's some examples here on how we're going to write interval notation. And here's an important idea. The interval notation is always written with the lesser value on the left. The smaller number is always on the left. That's how we think about numbers, whether it's in the x direction and the y direction. Smaller numbers always start us off, and then we go to higher numbers. So as an example there, x greater than 3. If I were to graph this on a number line, I would know it looks like something like this. Open circle and to the right. I can write that as an interval of 3 to infinity, because it never ends. It's going to keep on going forever. The second one, x is less than negative 4, I can put negative 4, an open circle, and it goes left. So the difference on this one is that now we're starting at negative infinity, because it's going to keep on going in that negative direction forever and ever and ever. Eventually, we're going to stop when we get to negative 4. Again, going from the left to the right. And then we do the same thing when we get to 2 and 5. So if I have a number line here, 2, 5, those are both open circles, and then in between. So again, our smaller number is the 2, the bigger number is the 5. The difference is when we get to a problem like this with the 4 and the 6, because the 4, if you notice, has that less than or equal to sign with it, which then gives it a bracket versus a parenthesis. And so that's really a key point in the interval notation, is when do we include that value and when don't we? So as a couple quick examples here, we have like number 5 here, which says, write the inequality 7 less than or equal to x less than 9. 7 is my smaller number. 9 is my bigger number. Because I have that less than or equal to sign attached with a 7, I'm going to bracket that. And then on the 9, I just have that less than symbol, so it's a parenthesis. 6, we have x is greater than negative 9, so I'm going to put negative 9. And that's because it's greater than, we're going to go up to infinity, and parentheses on everything. And 10, we have numbers that are smaller than 2, so 2 is our big number, that's where we're going to stop. And we want numbers less than that, negative infinity. And so that's how we're going to use interval notation. One more quick thing though, when we're talking about all real numbers, so everything works, any number we could possibly think of, the way we're going to write that in interval notation is from negative infinity to infinity with parentheses. So if we start looking at graphs, one of the things we want to know is about domain. And domain, again, is all the set of the inputs of a function. If I'm looking at linear equations or quadratic equations, what I want to know is, are there any restrictions on what I can plug into a function? Could I take a number and could I square it? Can I take a number, multiply it by a fraction, and then add or subtract something? And the reality is that there's no restrictions on what I can plug into a continuous linear or quadratic function. So my domain for those type of functions is always going to be all real numbers. So any linear or quadratic function, the domain will be from negative infinity to infinity. No restrictions. If we look at linear graphs, if we're talking about range are the outputs. These graphs are assumed to continue on forever. So if I continue this one up in the positive direction, it doesn't look like there's any value for the output that I would never be able to get. You know, eventually I can get up in the millions if I wanted to. It's going to take a really long time, but I can get there. And same thing in the negatives. Negative 3, negative 8, negative 10, and so on. I can get those values for my output. So there's no restrictions on the output. So for a linear function, this only works for linear. The range is negative infinity to infinity, only for linear. For quadratics, it doesn't quite work so easily. What we first have to do is figure out the max and the min of the function, and then from there we can extend that out to range. So we have three graphs here that are all concave up. We have three graphs down here that are all concave down. What we're asked to do is kind of make a connection here. And if you look at how it's being described, a graph that's concave up, we've got minimum values listed out. Minimum value is 0, -1, and 1. But concave down, now we're referring to that point as a maximum value because it's a definite high point. So if a graph is concave up, we know it will have a minimum value, and that's whatever the y-coordinate is of the vertex. For concave down graphs, we will have a maximum value, and again, it's whatever the y-coordinate is of the vertex. But now again, it's at a high point instead of a low point. So given a couple graphs, we'll do a couple quick ones here. Let's see. Oh yeah, there's some good ones. This first graph here is concave down, so the graph is going to open down. And we know that we are going to then have a maximum value, and it's going to occur here at that high point. The value is 3. Looking at graph at number 3, that graph is concave up, so that's a minimum value. It's got a low point, and that occurs at -1. Where it gets a little bit tricky is when we're actually on the axis, the x-axis, because the temptation is to give the x-coordinate instead of the y-coordinate. Again, a graph that's concave up has a low point. The value is the y-coordinate, so it's 0. And we can do the same for the equation. The nice part about the equation, if it's in vertex form, is that we have the y-coordinate specifically listed out here. We can tell concavity based on the number in front of the x squared term, or the parentheses as it were. So here we have a 2, that means that graph is concave up. A -1 means it's concave down, and so on. -3, concave down, and so on and so forth. So we can grab a couple of these and do the same thing, but now we're talking about the vertex form of the equation. So on this first one, we have -2 times the quantity x plus 3 squared minus 4. Because it's -2, that means it's concave down, so it has a max. And that max is the value right here, -4. Number 6, this graph, we don't have anything written in front of the parentheses, so my assumption is that's a 1. And so that's concave up, a minimum. We have nothing written after the parentheses, so that's assumed to be a plus 0. And so that would be my minimum value. On 5, we don't have that set of parentheses. That's no big deal. We're cool with that. We've got a -2, so that's opening down, so maximum value at 3, or of 3. So then how does this tie into range for quadratics? Well, if the graph is concave up, again, we know we have a minimum value. So if we're going from the lowest value to the highest, the lowest value is that minimum number, and the highest, well, it never ends. It goes up to infinity. We're going to put a bracket there because that vertex is actually part of the graph. It's part of our range. And for concave up, the minimum value is the first part of our range with a bracket, and the second part is infinity with the parenthesis because it never ends. Versus concave down, we now have a defined high point. The range then is from -infinity up to whatever that high point is. -infinity up to 15. -infinity up to 2. So on the graph of, I don't know, let's do one we haven't done, on number 5, that's a good one. So we have the graph here, and again, it's concave down. We have a maximum here at 2. So my range then, my lowest value is -infinity, never actually gets there. My highest value is 2. 2 is part of the vertex, so I'm going to bracket it. And this part will be parentheses. On number 6, we have a graph that's concave up, so a defined minimum value. And that minimum value is that y-coordinate of 1, and then up to infinity. And so that's how it's going to work when we're dealing with the graphs and figuring out the range. Same thing when we're looking at an equation. Again, figure out, is it concave up or down? What's the minimum or maximum value? And then find the range from that. A question like number 2 we know is concave up. So we're dealing with a minimum value. And that minimum value is 3. And it goes to infinity. Bracket the 3. Parenthesis around infinity. Number 5 is concave down. So that means there's a maximum value. So we're going to start at negative infinity and go to 3, parenthesis there, and bracket there. Again, domain is a set of all your inputs, and the range is your set of outputs. For linear equations, the domain and the range are both negative infinity to infinity. For quadratics, your domain is negative infinity to infinity, but your range depends on the graph and depends on the equation. And you can pick that out knowing the concavity and the value of the y coordinate of the vertex.